50, replicating it at 150, similar, replicating it minus 50, minus 100, minus 150, you will get this, isn't it? You will always get two triangles inside there. And you add it up, become a larger triangle. Then this one, 100. Then you shift 150, which is what I just done. Same. This one, when I shift here, there is one triangle here. But this time, that one shift, this side also another triangle here. Of course. Isn't this a summation? Minus infinity to plus infinity. Right? So this height, because of this formula here, it double. You can see it's double here. You can see it's double here. Alright? Okay. Huh? Alright? Okay? You can see it's double here. Times the 50. So this height here will be 50 times double is 10. It's 10. 500. The height is 500. Because of the convolution. Yeah. And the doubling occurs here. Right? Five plus 5, this is 5. Double becomes 10. Right? Right? Becomes 10. Originally it's 5, becomes 10. And then this 50 has to be taken into account. So it's 500. So that's part B. Don't shift here, cut there, shift there, cut there. No, not like that. Why not all? The formula says all. Right? The formula says all. Okay, part C. Can the original signal xt be recovered? Can the original signal be recovered? Yes. Because the original signal was this guy here. So if I have a band pass filter here, I can recover it. And the band pass filter, this one is at 30 Hertz to 70 Hertz. I can recover it. Right? But you have to use a band pass filter, not a low pass filter. Yeah, that's the scaling. Scaling does not distort the signal. Amplifying and attenuation.
这哪一年的？16年、17年。
I'm not converting. The question never asks you to convert. The question asks you whether, given this sample spectrum, can I recover back my original signal, which is this guy? And you can by using a band pass filter.
变成10是吗？
That is the question.
因为它本来就有这么一个在这里是5嘛，然后你考完了以后，两个三角形加一起就变成2倍。
Both. Duality says if this is tri, it means this is sin squared. If this is sin squared, this is tri. Duality. Correct? Rect is sink. If this is a sink, this is a rect.
So, the band pass filter, right, you XS visit times another vector.
Yes. So to recover it, you will take, suppose the output is Y lah, will be XF times HF. This is the band pass filter.
So HF is syn or
Rect, the blue one. Any other question?
so if I convert from also say rect F in here time domain is syn or calculation.
No. Because you are filtering out this guy will give you back XF with a multiplier. Let me call it A. That's what happened. Because you're filtering out those two triangles at plus and minus 50.
So in this case, I need to find what is the two triangle, the x.
Actually, it doesn't matter. She's just giving hypothetical questions right now,
Yeah.
which is not in the question at all. She's just thinking of, she's so afraid. What if they ask this? What if they ask that? What if they ask this? But the question never asked this. She's scaring herself. Yes. So when you do this, you don't go and do the rack and sink anymore because you know you're filtering out and the result is this guy. You know that this is the output with a scaling factor of A. To get back there, yeah. Right? Okay, so don't scare yourself. Okay. What's the second question? This one. Question 4. Okay, let's see what question 4 says. The complex envelope representation of a radio frequency pulse is given by this guy, okay? And theta is a real constant. Find the total energy E of xt. Okay, that's the first one. So this one, it will be easier if you find the total energy in the time domain. Why? Because you know that the total energy E correct? That's the total energy. Okay? And your total xt is equals to rect T over 10 e to the j theta. So mod xt is just rect T over 10. Correct? Because it's space. Disappear. So E will be integral from minus infinity to plus infinity of rect T over 10 dt. Correct? But rect is a width of 10 seconds. That is from minus 5 to plus 5. So you can change this from minus 5 to plus 5. Okay? Of rect T over 10 dt, which is 1 times dt. Because in here, correct? So I'm sure you can do this. Remember? Huh? Yeah? So that's part A. Okay? Any questions?
Normally total energy to find the pulse, is it a finite time?
For a pulse, it's always finite because beyond a certain time is all zero. All pulses are energy signals and they will be finite. Whatever the shape of the pulse.
So can I, what's the difference between the ESD and the Dirac?
What's the difference between what? Sorry?
The ESD, right, is
The ESD is spectral density. Spectral density is this guy. That's what it is.
Is it only in frequency?
Do I see T there? Okay? That's what it is. So second part. The energy spectral density, EXF, and the first now bandwidth. Okay? Okay? So, right. So first of all, you need to find what is XF first, isn't it? Right? Since XT goes to rect T over 10 e to the j theta. Alright? This is just a complex multiplier. There is no time here. It's just a complex multiplier. So XF, the complex multiplier will still be there. It's just a complex number. Doesn't change, right? If I didn't put a complex, I put 3 here, you will put 3 here also. Times right? It's just a complex number. But I know that once you saw it, hey, what's so funny? I never seen her multiply before. Every time in the class, every time the notes is only a constant. It's just a constant. So far we've seen the imaginary part is 0. Right? But it really doesn't matter. Everyone with me here? Therefore, right? Right? We haven't found the bandwidth yet. We only found EXF. So if I plot this guy, alright? If I plot this guy will look like that. Because it's a sinc square. And where are the nulls? Where is the null? For sinc? Sinc of any integer number is 0 except when n equals to 0. Huh? Right? That's the sinc function. So when will the first null be? When this is 1. When will this become 1? When f is 1 over 10. So this is at 1 over 10. This is at 2 over 10. This is at 3 over 10. Minus 1 over 10. Minus 2 over 10. Minus 3 over 10. Correct? These are where the nulls are. So he's asking you, what is the first null bandwidth? Scalar. That's the first null bandwidth. Okay? Alright? Huh? Any question?
Total energy can it be?
Come again.
If you find total energy, can it be?
You can find total energy either in frequency or time. That is the Rayleigh's energy theorem. Either way.
But the result is same, correct?
Same, of course it's the same. That's the Rayleigh energy theorem.
It's a real number, correct?
Because you mod it already, right? There's no imaginary part yet. Once you mod any complex number, it's just a constant number. Right? You mod it, yeah.
First one, write the square, normal square.
Which one?
xt.
This one?
The total energy in time domain.
No,
No,
the
no,
first,
red.
first line.
The energy equal to minus infinity.
Yeah, this one?
Yeah,
Red square is still red.
yes. Yeah, your name.
Yeah, rectangle you square is still a name rectangle.
Okay.
Right?
Okay. Yes.
Okay. Any other question? Okay, and go to part C now. So, suppose we delay t by tau seconds. Okay, how does this affect the value of E, EXF, and B now? So in other words, we delay it by t seconds. That means now, instead of having xt, the delayed value is x of t minus tau, correct? We delay it by t tau seconds. So if you do this, xdf will be xf times e to the minus j 2 pi f tau, isn't it? But everything is in magnitude, so it will not affect it. This will disappear. You see? Magnitude. So the e term will disappear, right? Because you're finding magnitude. That means if that's the case, E will still be the same. EXF will still be the same. And of course, BN will still be the same. Because here, same. So E will still be the same. Bn will still be the same. Got it? No? Why would you go up? I just showed you there. This disappeared. This disappeared. This is this guy. This is this guy. Why must it go up? For the delayed version? No, I have just proven you mathematically here they are same. But you don't believe this question, this answer? Yeah, square is still the same one.
You mean the same function square?
I didn't say anything about sinc function. I don't know why you are so fixated with racks and sinks here. There is no sinc here. Alright, I haven't even done any Fourier transform for that matter to work out this guy. Okay, I'm still talking about the big X and the little x. Alright, the question is saying if the little x is delayed by tau seconds, which means I have this signal now, delayed by tau seconds. Will the energy be the same as for xt? Is the energy, you see, you read the question carefully. He's asking you, is the energy, is the energy of the xd signal, is it the same or not as ex? E for the x. He's asking you that question. Then he asks you, is the E D, this is the spectral density, is it the same as E of xf? That's what he's asking you. Is the Bn of xd, is it the same as Bn of x? Those are the three questions it's asking you. So please read the question carefully. That's what it's asking you. I do not know and I don't understand why you have interpreted the question differently. Because both examples to example form, you have both times interpreted the question differently. That's very dangerous. So you could give an answer, you're not answering the question. So please read the question carefully, okay? So that was the question for part C. All right? All right, another question? Okay, I will jump to somebody else and then I'll come back to your last question. Anybody else? Another question?
How do you define this question? How do you define this?
There's no definition, just follow what the question is telling you. It's not a question of definition here. It's whether you understand the question or not. Alright, so read it carefully. What this question tells you is that I'm given a signal xt. Then he asks me to find the energy of this signal. Very straightforward, which is that formula. Right? Okay? So of course there is an easy way to do it and a hard way to do it. Easy way, this is the easy way in the time domain. Now if you had done it this way, in the frequency domain, you will have a single squared term. You'll be stuck. You cannot find a final answer. How to integrate a single squared term? Of course it can be integrated, but you have to do integration by parts, which I think most of you have forgotten already. Because you've got a numerator and a sinc pi x over pi x. That's why you have to do integration by parts. Now, if your maths is very good, you should arrive at the same answer, which is 10. So you have to be smart about it now, right? So obviously, it's easier to do this in the time domain. So it's nothing to do with definition here. It's whether you understand the question, right? So the first part is to ask you, what's the energy? Calculate it all. Second part is spectral density, which is this guy, right? Okay, energy supply. And the first noun, okay, first noun, this guy. Now, maybe a lot of you will not know how to do this. What is first noun? Never taught us before first noun. Actually, we have taught you. It's just that we didn't give you a tutorial question for it, that's all. We thought you go back to your notes, we did mention first noun. But whether you understood that or not, to apply it here is another matter. We covered at least 3 definitions of bandwidth. At least 3. The first one is your 3 dB bandwidth. There were examples there. The second one was what we call the 98% containment bandwidth. We have done example there. Right? Only this one now, first now, we didn't do an example. But you have learned it. It is in the lecture notes. Okay, so that's the second part. And the third part is this part here, the blue one here. So what the third part is trying to test you is whether a delay in the signal will affect the total energy, the spectral density, and the bandwidth. And we have proven to you here that it will not affect, because when you do all these 3 things, it is based on mod capital XF, the magnitude. So phase all taken away, what you don't care. So therefore it won't affect the total energy, it will not affect the spectral density, it it will not affect your bandwidth. Okay? So that's what the question asks you. What is the definition? There is no definition. It's just a question. It's just a question. But it tests you on whether you understand what we have covered for energy. Okay?
So in this case, the delay will not affect the
What do you think?
yeah
Energy.
the energy bandwidth and the EXF, ESDF are all the same because the
I'm proving it,
formula
right?
is
I wrote it down mathematically
Yes,
here.
yes.
Unless you don't believe it.
No, I just the conclusion
Yeah.
for big memory.
Right? You've done it mathematically here.
Yes.
But we shift the position, B also never.
No, it doesn't. Because the energy is still the same.
他是想
Because
因
the
为
spectral
两个
density is still the
绝
same.
对值以后，那个 E 就不见了。
They also
那个 E 不见就不会影响，因为 E 是 phase shift，就会看着这样。
Still the same square.
对
Right? Still the same square. So the now is the same position.
就可以，
formula
它所有的都是这个
Right?
不是，你看这，
Still the same
我
square.
先抄一下。
Okay, let's move on. Okay? Yeah.
Well, general question.
Sure.
In the quiz or the past year paper, we've seen given a signal, awkward shape. The quiz, I think we have one.
We like awkward shapes. Yes.
Awkward shape. So that's one question to tackle.
Yeah.
So often the question will come up with expression.
Find the Fourier transform or something like that.
他应该是从这个，
And at the
这
same
个
time, they
phase
put
shift，
another
它
graph.
是 phase shift 是这个嘛，然后你再 transform 过来就变成这个嘛，然后就，然后你再决定这个就不见了。
It depends on the question.
So what is the typical, in this case, how, what should we understand from this?
Okay. So
Maybe we start with one simple one.
So always go back to first principle. The first principle is that any signal can be represented either in the time domain or frequency domain. Right? That's what Fourier is all about. In the time domain, we call it little xt, for example. In the frequency domain, we call it capital Xm. So it depends on what the question is, because your query right now is so general, it covers the entire 6 weeks of the course.
Maybe we start off with, let's say we have a triangle or a rectangle with a cone.
Okay, it doesn't matter what is the signal. So you want a triangle. Everybody loves
No,
triangle.
you need to define the signal. Or it could be a triangle in the frequency domain.
Then it is a spectrum. Then it's an XF. Suppose you like triangles. Okay, we all use triangles here. So this is time domain. So now I have a triangle here. Okay, let's say -1, 1, and 1. So this is xt. Now I can have a triangle in the frequency domain. Doesn't matter. Same thing. So this is xn. What do you want to do with it now?
Expression.
I'll just give you the expression. It's written on the board. What do you want?
Oh, okay. Class option. Okay. Then we need to spice out a little bit.
Okay, let's spice it up.
Spice out a little bit with another, maybe I don't know, awkward shape. Yeah.
Okay, yeah, no problem. So I don't have to anymore.
Very much depends on your imagination.
Right.
Yeah. That's all the exam question come out, right?
Yeah, you must imagine now. Okay? Suppose I have this. -1, 1, 1. So xt, this is again time, will be rect t minus tri t, right? T over 2. Correct? Same thing. Now it is frequency. This is f. Minus 1, 1, 1. So xf, again rect, f over 2 minus tri f. Okay, what do you want? Same thing.
Right minus inverse.
Right? No big deal.
Okay. Now next thing is transform that
You want to transform this?
yeah.
You want to transform this? No problem. So this is xf. Right, what do you get? 2 6 2f minus sin squared f. So this is the transform. This one transform give back your time signal. Again, 2 sin 2t minus sin squared t. Okay, so transform review.
Okay.
It's just a change of variable.
Okay. Let's say.
Okay, spice it up some more.
Okay. Let's say we need to. Okay, what thing is from? Energy.
你看这个，它这个是减，
Wait, huh?
这个是减了再变成乘
Triangle is sin squared.
这个也是减。
Half-wise. There's no period here. It's not a periodic signal.
为什么？为什么
So
变
you're
成
using
点？
all the wrong
这是
terminology.
减的，
这个是个
Yeah.
点，
What you're really trying to say is not the period. You're really trying to say the width of a triangle, which is nothing to do with period. Wrong words. Yeah. Try one.
记得不行。
One based on one. Or rect is based on the width. That's why it's got two there. Spicy friend, what is the next spice?
Let's see where. Yeah. I think this one is a bit too complicated for calculate energy.
This one?
Yeah.
No?
No. Huh?
No? You do it in the time domain? It's just that you have to split it up into two integrals.
Split up into two integrals.
Yeah. Integral on the positive and the negative. But since they are symmetrical, you can times 2.
Because it's identical.
Yes, times 2, that's all. And that straight line from there to there, that's it. Square it. No big deal.
Can I simplify by just noting down the because the variation is again.
等一下，我想到一个，
No.
像你问那个男的，他
Area of the square of
那
that.
个按照
Mod xt squared. So you will get a t squared inside your integral. It becomes a parabola there. Okay?
What about
It has come up before. Same shape. If you go back the past, it has come up before. Yeah.
how about 3 dB bandwidth? 3 dB.
3 dB bandwidth, then you look at this guy.
3 dB look
Right?
at this guy.
Then you have EXF. Is this whole thing squared?
Whole thing square.
Yeah. 4xf squared.
Okay. How we cannot
Correct? Huh? This whole thing squared.
just leave it like that or
Yeah.
leave it
So
like
you
that?
got A minus B. So you square what you get. A squared minus 2AB plus B squared. So 3 terms there. Then you find what is EX naught. That is in the middle here. Alright, from here, you find what is Ex naught. And the 3 dB will be Ex F 3 dB over Ex naught is 1/2.
Okay.
Now, I would not recommend that you do it this way because you will get error there. This is the same as saying mod X at F3 dB over mod X0 equals 1/√2. Now, this is easy to do because you don't have to square it.
What's the top one?
This is this parallel because what's the definition? Ex is mod X squared.
The mod of 3 dB.
Yeah, mod 3 dB, same thing. 3 dB. Right? So what is Ex naught? Ex naught is, this is 2 minus 1. It's 1. Sink of 0 is 1. Sink squared of 0 is 1.
Square root of 2 plus 2 square plus 1 square, is it?
Isn't it?
More of 1. More of 1 is 1.
Yeah, mod of 1 is 1. You sound unbelievable. Right? Okay, so what you're going to find is that if you want 3 dB using this formula, it will be 2 sink of 2 F 3 dB minus sink squared F 3 dB, okay, divided by 1 equals 1/√2. You're supposed to solve that. Right? This is this guy. This is this guy here. This guy here. This guy here. Right? So I'm just taking this hypothetical spicy case.
Typically,
But
I think it's 1
but the procedure is the same. The procedure is always the same, irrespective of what is the shape of the signal. The procedure is the same. The only thing changed what is the shape of the signal, that's all.
I like to see old triangle always come out.
I don't know, we like triangles. Good for you, less signals to remember. Yeah, but it really don't matter. It don't matter. What is important is whether you know the procedure, right?
So the matching formula is that take the mod formula equal to
Yeah, this we have covered already. This is in chapter 4. I think. I think it's in chapter 4. Under energy and power. All covered already.
它直接 copy 这一个到这里，因为它直接是绝对值跟后，
Right?
所以就不用这个。
Anything more to spice up?
直接把这样 copy 下来就可以，只是换成 F
哦 maybe to make it that one
F
is
我已经算过了，
sampling
是这个，不是。
Alright, go to another person. Any question? Another person?
X 里面
How about the impulse response and step response?
他写了一个 X 里面，他写
How
了
we going to choose those?
Okay. Okay, the question is, we learn about impulse response, we learn about step response. How do we use it? Is that a question?
当 F 里面的时候，X 和 这个我就要
Usually in practice, you use the impulse response to identify what is the transfer function. Okay? Because when you why do you take a picture?
I don't have a camera.
Oh, you don't have camera. This is two sink here. Alright, anyway, what I was going to say is this.
Somebody another about that.
Oh, okay.
You can turn on.
Alright. We know that the output is the input times the transfer function, right? So if your input is an impulse, xs is equal to 1. Therefore, ys will be gs. So that's to discover this guy. We use impulse. Right? When you have a step, so this is for impulse. This is impulse. So when you have step, xt is equals to some number, a times ut. That's the step. A is a constant. So xs will be a over s. And ys will be gs times a over s. Okay? When do we use this? We use this for many practical systems. You turn on the switch. Alright? You complete the circuit at a certain time. That's a step function. Right? Whenever you turn on the switch or complete a circuit, there is an input step function there. So that's when we use it in practical cases. Alright? Follow?
complete function
How shall we
turn on the switch step function会出现 complete function
restart?
Then you have to work this out. Whatever is GS, first order system, second order system. Then we went through all the maths, went through all the derivation, under them, over them, critically them, and them for second order system. Correct? First order is exponential. Right? But you have to work through the details by factorizing this, etc. So that's when we do that. Impulse and step.
Which part use Laplace?
All use Laplace.
No, I mean, except the input, the system use Laplace.
Time domain is T. S domain is Laplace. And why we use Laplace? To get rid of the differential equations. That's why we go to Laplace. So all the derivatives in the time domain, when you do the Laplace transform, the differentials go away. Second derivative is 1 over s squared. First derivative is 1 over s. Correct? And it becomes from a DE, differential equation, to an algebraic equation. So we say that in general, you have something like this. Alright? A to the n, y, oh. This is a differential equation in the time domain. I'm just taking a general form. When you take Laplace, this becomes, assuming zero initial condition. Right? That's what we say. So no more differential, just an algebraic equation. So that is in chapter 6, the first lesson that I taught you. Correct? So if you want GS, it's a transfer function. Okay? Yeah, you've got to factorize it. I won't show you the whole thing. Okay, you've got to factorize it. Okay? Yeah. Can I erase that?
Yes, please.
Alright, another question, please.
Can you give me a general idea about step response for first order system and the second order system and the time constants about it?
Can you repeat your question?
The step response for a first order system and second order system and the time constants related to that.
Alright. For a step response. For a step response.
Yeah, for step response.
Okay, so if you have a step response, the input is some sort of thing like that. Actually, I think in the lecture notes we call this R. Right? R is a constant. Correct?
Yes.
So your XS,
Always. Yeah.
okay? Now, GS, first order, let me call it G1 now.
Okay.
This is a generic expression for a first order. Right? So you can change this. I take out a T. Okay? So my output for a first order system is G1S times XS, which is K over tau. Alright? So you will see there are two factors. There are two factors. So this one will give us something like this. Right?
Oh.
Two factors.
Yeah.
Right? So if you do the inverse Laplace, and then of course you have the K over T in front. Okay? So if you do the inverse Laplace, this guy, the K over T is still here. This guy will give me something like this. A1 e to the minus S over T. Correct? And this one will give me A2. On the west.
You reverse why there is S still there.
Hmm?
The
Okay,
first
for the
equal.
A1, since we should be able to see.
Oh.
Right?
It's T over T. T over cap T.
Yeah, so this is T.
Ah.
Right? Huh? So if you plot this, when T equals to 0, e to 0 is 1, right? So you get A1 plus A2, right? So let's say this is A1 plus A2. Suppose it's A1 plus A2.
Make it over T.
When T equals, little t is 0.
Oh,
E to 0 is 1.
K over cap T.
Little t over capital T. When little t is 0,
No, K over T.
yeah, K over T is still here.
So,
Yeah, with the K over T.
so this is, okay,
So this is the starting point.
starting point.
Then when little t goes to infinity, e to the minus infinity is 0.
Yeah.
So this guy will decay like that.
Oh, that's because E.
Right?
Yeah.
And what is this time constant capital T? That is when it reaches 0.632 of the final value. So the final value is here. So it's 0.632 down. This value here is the time constant.
0.6, 0.6.
32 of the final value. When it reaches 0.632 of the final value.
That's because small t equal to capital T. Okay.
Is it always 0.63?
Because it's 1 minus e to the minus 1.
Yes.
Always.
这边是 A1，
Guaranteed 100%
So this is
刚刚这里
of the final value.
final value.
Okay, whatever is the final value. So you start from your beginning, you go 0.632 down.
612。
623.
This is the response of
但是问题
a
刚刚因为这个等于0嘛，
step
那
function.
这个还是等于2嘛
这个 T 等于
意思是你
T 等于
response
infinity 这个整个等于0嘛，对吗？
time constant there.
对吗？A1 等于0，这个 A2还是2吗？
No?
这等于负1的时候，
Well, the graph for this, let me see the graph.
你问哪？
When this goes to 0,
对 T 等于0在这里嘛 T 等于 infinity 的时候往下走，但是你 T 等于 infinity 1 minus infinity 等于0嘛，对吗？0 times A1 就等于0嘛。
没有没有，这个是T 等于大 T，
Right?
小 T 等于大
This
T。
will go to 0. Suppose this is A2 lah.
的你是讲那个点是吗？这个大 T。
A2 lah.
A2 supposed to be a constant.
So it will go all the way down. So whatever is 0.632 down here. Down from up in reaching this part here. Okay? That's the concept.
就是这。
Okay? Huh?
这个是 A 等于
So this step response
Step response.
always
Always.
the final the graphic always like this, right?
For a first order system. Okay?
First order system.
First of all, which is all in your notes. Plus in the formula sheet. Okay?
Sorry. But this one's close.
Yeah, because I haven't put in A1, A2 yet. One of them is actually negative.
So in this case,
I'm drawing
A1
all,
is
assuming
negative.
every A1 and A2 is positive. Huh? I haven't worked out the whole thing. I'm just giving you the concept.
Oh, okay.
Alright? So this is first order.
Yeah.
The
Okay.
graph supposed to be a step, right?
Yeah, the input is a step.
Yeah. Input is step.
Okay? Are we okay with step function for first order?
Function for first order and
So are we going through the quiz question?
No, I haven't finished the question yet. we will try to, but probably we have to do it in a makeup lesson. Okay? So now, let's look at the second order. Alright, this is first order. Okay? The input is still the same. Your xt r times ut. So xs is r over s. Now for the second order, the generic function is k omega n squared over s squared plus 2 zeta omega ns plus omega n squared. That's a generic function. You seen this before, right? Huh? Commit to memory. Cannot memorize? Formula sheet given to you. Alright, so your output correct? Huh? So, we said there are 4 cases for this, depending on zeta. 4 cases. Zeta less than 1, zeta greater than 1, zeta equals to 1, zeta equals to 0. 4 cases. Under them, over them, critically them, under them. Okay? So for each of these 4 cases, they will behave differently here. For example, let's take a simple case, and then zeta equals to 0. Okay, so in this case, the y2s will become k omega n squared over s squared plus omega n squared. Right? Which becomes k omega n times, if you do the inverse Laplace transform, inverse Laplace transform, you get a sinusoid. That's your output. If zeta is 0. Alright? When zeta equals to 1, this guy is 1. Okay? From here, you get that. Correct? Correct? 2 real poles. Yeah? 2 real poles. Any oscillation? No oscillation, right? Huh? Repeated pole, right?
Yes.
At minus omega n, right? Which is a real number. Okay? So this guy over here will give us something like that. Some E term. Okay, I don't have the full expression for you. It will be something that looks like this. It will be something like that. Yeah? You have the exact expression inside your notes. Correct? Yeah. So that's inside here.